Okay, so let's do an example. The example we're going to do is question 1 on page 51. So this question is simply your bathroom scales question. The principal operation of a weighing machine, shown here in figure 3.11, M is 50 kilograms and K is 100 kilonewtons per meter, is the measurement of deflection X for a given weight. Okay? If a mass M, big M of 200 kilograms is placed on top, find the expression for T. And so we've got a system where we've got big M up here, so that could be one fat bastard, one fat person, little m down here, you're going to be pretty big if you weigh 200 kilograms, and you've got some pretty heavy scales if they weigh 50 kilograms. But let's not worry about the complexities. We've got this mass and it ends up landing on our mass here, yeah? So it moves down, drops down, and obviously then X will deflect in this direction. And we know that M is 50 kilograms, big M is 200 kilograms, and K was told to be 100 kilonewtons per meter. And we've got to find a solution for X. A. What's the forcing function? What form is the forcing function?
Mass.
Yeah, it's the mass. What's that? Does mass vary with time?
200 times gravity.
Yeah, but does it vary with time? What's the form of it? I don't know what the value is. It's a... yeah, it's a constant, isn't it? Yeah? That's, the form of the forcing function is a constant. It doesn't vary with respect to time. And so our solution, we found it. Okay, what's F naught in this case? Sorry? Big M. Okay? Sorry, big MG. And so we can actually work out some values. Let's work out omega naught. That's root K upon which M? Small m. And if you do those sums, you get 44.72. And so we've got X of t equals big M G divided by K, 1 minus cosine omega naught t. Now mg, that's going to be 200 times by 9.81. Divided by 100 times 10 to the 3 times by 1 minus cosine of 44.72 t. And if we work this quantity out, that comes out to be 2 times 10 to the minus 3, 1 minus cosine 44.72 t. Now some of you who've got old bathroom scales, you'll know when you get on, the thing oscillates backwards and forwards, centred around your actual weight, doesn't it? And then that oscillation dies away and you end up actually reading your weight. Well, that's essentially what's going on. There's no damping in this equation. Obviously if there was damping there'd be a decaying exponential right here, which is that dying away term. But that's what it's doing, it's oscillating around that weight. And obviously for that 200 kilograms on this scale, okay, the deflection is 2 millimeters with that stiffness and the mass of the actual scales themselves. Okay, so it detects 2 millimeters and the thing's going to oscillate around that point, that 2 millimeters point, backwards and forwards. Okay. So the dial on the scales, like I said, when it's going backwards, if you've got these old-fashioned scales where it's a mechanical device, you find that it oscillates backwards and forwards. That's also why when you've got these digital scales, you step on, you've got to wait a few seconds for it to actually come up with a value. That's because the thing's oscillating backwards and forwards. And it's waiting for that value to become a constant before it actually shows you your weight. So that's part A of question 1. Part B, plot x against time. We did this on the board, so I'm going to repeat it here though. If we plot cosine 44.72t against time, that's 1, that's minus 1. We end up with something that looks a little bit like this. If we plot minus cosine of 44.72t, we get something that looks a bit like this. So it's just this one. It's this one upside down. And if we put 1 minus cosine of 44.72t, okay. So you get the whole thing is added 1 to 1. So this could be minus cosine omega naught t plus 1. So you just add 1 to the whole lot. And then obviously if we were to do the whole thing, 2 times 10 to the minus 3, 1 minus cosine of 44.72t, we end up with that's 2 millimeters and that's 4 millimeters. Just drawing some points so I can know where to draw. And so on. So that's our solution. What's the period? What's this value here? Out of interest. You should know this equation by heart. So it's 2 pi divided by 44.72, which I'm sure you can calculate if you had a calculator. And part C says, discuss the implications of your findings. And what I mean by that is say something to the nature of, it's say oscillation centered around f sorry, mg upon k. Okay. Offset sinusoid. If you included damping, you'd obviously have something that decays with respect to time. So if I mark the value. You have this sort of decay with respect to time, so that's with damping. And obviously your period would be divided by omega d, not omega naught, because you have the damped frequency. So we'll do question 2, but instead of part A is basically the workings that we went through in the lecture, and you can go through them yourself. But part B, let's look at that. Part B, we've got the solution. X t is f naught upon k minus m omega squared times by sine omega t plus minus omega over omega naught sine omega naught t. Or that obviously could equally be just a minus omega over omega naught. It's up to you. Now part I go on to discuss the forms of the response for omega is much, much bigger than omega naught. So if omega is much, much bigger than omega naught, this term becomes much, much larger than 1, doesn't it? Yeah? Omega over omega naught. If omega is much, much bigger than omega naught, then you get a value that's much, much bigger than 1. So you get, this term is going to dominate, isn't it? Yeah? Whereas this term is going to be quite small relative to that one. And so, if this is the case, then you have, if we call this term alpha, and this term beta, just to refer to them, okay? When this is the case, beta dominates. So you have an oscillation with frequency omega naught. With a small ripple at omega. So you end up with an oscillation at this frequency, because this term dominates, with a small ripple at omega. Yeah? So basically you get this big omega, which is the natural frequency of the system. For you guys it's this way, okay? But instead there'll be a small ripple at the natural frequency, so you end up with this sort of response. Part II, when omega is much, much smaller than omega naught. Which term dominates now? If omega is much, much smaller than omega naught, what does that fraction turn into? It turns into something very small, doesn't it? You get something very small over 1 or whatever. Okay, so which term dominates? That one. Okay, so you get the same sort of thing. Alpha dominates. So you get an oscillation. At omega. Okay. So when your forcing function is much, much larger than the actual natural frequency of the system, you have an oscillation at the natural frequency with a small ripple in your forcing function frequency. But when it's much, much smaller than omega naught, you get your forcing function being the dominant thing with a small ripple at omega naught. Now if you remember back in chapter 2, we looked at what's happening with the forcing function, and we saw that as omega goes, as your driving frequency goes to infinity, yeah, you remember the thing didn't, A turned into 0. The A approached 0, you had 0 amplitude. Well here we've got damping, we've got no damping in the system, so obviously the only thing that's going to affect that is going to be your natural frequency, okay? I. What happens when they're approximately equal to each other?
0.
Sorry?
Goes to 0.
No. We covered it, didn't we? When they're approximately equal to each other, you have a beating, yeah? And in a bit more words, phase drift occurs. Okay. And then IV when they're equal to each other, your driving frequency equals the natural frequency, what happens? What does the response look like? Solution above is not valid. As I said, this solution is only valid for where there's a difference in omega and omega naught. Okay? Where if they're equal to each other, that solution doesn't work anymore. Okay? And part C says, how does the response for a real single degree of freedom system differ from that described for B1 and B4? What's the difference? What is it? Notice I italicize the word real in the question. What's the difference between this situation and a real system? Damping, exactly. So in that solution, if we were to solve it for a damped system, you'd find that that sine omega naught term would have an exponential in front of it, and that exponential would be a decaying exponential that decays as time goes to infinity to 0. And so that damping term would disappear. And so for the case where omega is much, much larger than omega naught, you'd start off with beta dominating, okay, with a small ripple at omega naught, at omega, but that big omega naught term that dominates will disappear down to 0, and you end up with a small ripple in omega naught. At frequency omega. And that's what I was talking about. Well, if you're shaking something very, very fast, the amplitude of that shake is approaching 0 as the amplitude goes up to infinity, and that's what's happening. The natural oscillation will die away. Okay, to start with, you get the mix of the two, but that oscillation will die away. You end up with a very small amplitude of oscillation. Okay. And what happens with this, if you refer to the actual solution that's in your notes, as with damping, again you get a damping term in front of the omega naught frequency, okay, so that will die away to 0. But what actually happens is you'll end up, the thing's being oscillated at resonance, and so you end up with a big peak, okay, and that peak will depend on how much damping you've got in the system. The less damping, the more it approaches infinity. And resonance is bad, as you all should be aware. Well, it can be useful. In some cases it's useful, but often it's undesired. It's not what you're looking for. Anyway, so that's chapter 3. These solutions will be online in approximately 10 minutes. Okay. Before you all leave, okay, I've also, we've just done all the solutions to those questions in the notes. I've put some additional questions up on Blackboard. Okay, they're under they're in the course materials area, and they're to extend what we've done here. Okay, and those solutions will go online shortly as well. But those questions are up on Blackboard, so download them and take a look. Thank you very much.